Hi there. Welcome to the stoichiometry simulation. Here you will learn about Avogadro's number and how the molecular weight, mass, and number of molecules correlate. This simulation uses voiceovers. If you don't have audio, click the speaker symbol on the top right of your lab pad to switch to play mode. If you disable the sound effects, the lab pad will slide up whenever there are instructions to read. You can select what type of audio you prefer. Deselecting any of the options will mute that option. Click Continue to learn how to navigate through your mission. Using the lab pad is an important way to get the most out of the simulation. Is this your first time playing a Labster simulation? Perfect. Then let's get started with your first mission. Find the lockers and open one of them. Raise your lab pad for more information. Find a lab coat inside the lockers and pick it up. Well done. Remember to wear safety goggles in the lab to protect your eyes. Click on a pair of goggles to wear them. Raise your lab pad for more info. Enter the lab to start the experiments. Welcome to the lab. I am so happy that you're here. I have a problem and I need your help. We were going through the chemical storage room and discovered a chemical container where the label has been partly destroyed. Now we need to figure out what is inside so we can relabel it correctly. To figure out which compound it is, you will use the method of gravimetric analysis. Are you up for the challenge? Great. I like that spirit. By the way, you are walking in the footsteps of giants. The great Marie Curie actually used a gravimetric analysis to determine the atomic mass of the radioactive atom radium in her PhD dissertation. To perform a gravimetric analysis, you need to know how to balance a chemical equation. Let's see if you can do that. Go to the workbench. Take a look at the wall display and click it. The chemical jar was standing on the shelf of alkaline earth metal compounds, and the label still reads chloride. So we just need to find out which of the alkaline earth metals the compound is a chloride of: beryllium, magnesium, calcium, strontium, barium, or radium. Notice that all the compounds have the general formula XCl2. To find out what the unlabeled compound is, we will react it with a solution of silver nitrate. This is the reaction you see on the wall display. You will notice that the reaction scheme is not balanced. Balance the equation on the wall display. Click the Done button when you think you have it. Very good. You have balanced the equation. In a gravimetric analysis, you determine the amount of an analyte based on mass. Look at the equation again. Both chlorides and nitrates of the alkaline earth metals are very soluble in water, as is silver nitrate, but silver chloride is insoluble and will precipitate from the solution as a solid. By weighing the mass of silver chloride formed, you can calculate how much chloride was in the sample to begin with, and thereby figure out what the unlabeled chemical is. Look at the workbench. There you see the unlabeled chemical. This is a large jar containing 500 grams, so it is very unlikely that it is strontium or barium chloride, as these are quite expensive chemicals. And radium chloride is highly radioactive, so I think we can rule that one out too. Let's get started with the gravimetric analysis. You need to weigh out a sample of the unlabeled chemical. The mass should be around 3 grams. Put on a pair of gloves. Open the analytical balance, place a weighing dish inside and press stir. Click the unlabeled chemical to examine it. See, the label has been partly destroyed and now it only reads chloride. Click anywhere on the workbench when you're done examining. Place the unlabeled chemical by the balance. Pick up the spatula. Use the spatula to transfer 3 grams of the unlabeled chemical to the weighing dish. Place the spatula back in the beaker. Dispose of your gloves in the trash bin. Check out the digits on the analytical balance. You should write down the exact mass in your lab journal on the computer. Go to your lab journal on the computer. Note the exact amount of the unlabeled chemical in the yellow field in your lab journal. Now, we said that we could rule out strontium, barium and radium, so we have 3 possible compounds left: beryllium, magnesium and calcium chloride. Look at your lab journal, there are 4 different tabs, 1 general and 1 for each of the 3 different compounds. Check out the different tabs in your lab journal. Raise your lab pad when you are done. Are you done exploring? Notice that in each of the tabs you see the reaction of that compound with silver nitrate, and below the chemical equation is a scheme to calculate how many moles of each compound you have. You have to calculate the missing numbers. I have helped you a little and looked up the molecular weights for you, but for the rest you need to learn a little bit of theory first. Take a look at the wall display, and click it. Atoms and molecules are way too small to be seen, even with a microscope, so how can we count how many there are? You are right. We count atoms and molecules the same way we would count at other small atoms. By mass. Look at the wall display. If we know that the average mass of one corn kernel is 0.282 grams and we want to count out 100 corn kernels, we do it on a scale. 0.282 grams times 100 equals 28.2 grams. The same concept can be applied to atoms and molecules, only now the mass of one atom is so small that we need to weigh them out, not in hundreds, but in millions of billions. Just as eggs are counted in dozens. A dozen just being another word for 12. So atoms and molecules are counted in moles. A mole is also referred to as Avogadro's number. It is 6.02214 times 10 to the 23rd. That is a very, very large number. Let's try to visualize how large a number it is. Look at the 3 pictures on the wall display. The first picture is the Sahara Desert. Let's say that the layer of sand is 2 meters deep. The second picture is a shot glass of water containing 18 milliliters of water. The third picture is an iron bolt with a mass of 56 grams. In which of the pictures do you find the most particles? By particles I mean sand grains, water molecules and iron atoms. Yes, you are correct. If you dig up all of the sand in the Sahara Desert, 2 meters deep, then you will have a mole of sand grains. Sand grains are small, but they are huge in comparison to atoms and molecules. 8 mole of water molecules takes up only 18 milliliters. By drinking a glass of water you ingest more water molecules than there are sand grains in the Sahara Desert. Now you are ready to look at a very important equation. You probably know how to find the molecular weight of a compound by looking at the periodic table. Recall that the unit of molecular weight is grams per mole. That means that if you know how many moles you have of a compound, you can calculate the mass, or if you know the mass, you can calculate how many moles that corresponds to. Let's try a little game to see how these 3 concepts correlate with each other. On the wall display you can see 3 square buttons with the symbols N, M and capital M, and 2 narrow buttons with a multiply and divide sign, respectively. The first equation you need to complete is how to calculate molecular weight, capital M, from the mass, M, and the number of moles, N. As each part of the equation lights up, click on the symbol you think should be there. When you think the equation is correct, press the Done button. Remember that it may help you to think about the units. Calculate the molar mass, capital M. Very good. Now you have to figure out how to calculate the mass, M, from the molecular weight, capital M, and the number of moles, N. When you think the equation is correct, press the Done button. Calculate the mass, M. Excellent! You are very good at this. The final equation you have to figure out is how to calculate the number of moles, N, from the molecular weight capital M, and the mass, M. When you think the equation is correct, press the Done button. Calculate the number of moles, N. Awesome! If you want to know more about the equations you have just derived, please go to the theory pages. Otherwise, now it is time to put all your newfound theoretical knowledge to practical use. Let's move on with the calculations for the gravimetric analysis. Go back to your lab journal. From the mass of unlabeled chemical and the molecular weight of beryllium, magnesium and calcium chloride given, calculate the number of moles of each. Pick the correct formula in the drop-down menu to calculate the number of moles, N. Repeat the step for all three possible compounds. Yes, you've got it. Remember to perform the calculation in all three tabs. Yes, exactly. Yes, you are very good at this. Alright, let's move on with the experiment. In order to perform the gravimetric analysis, the sample of unlabeled chemical should be dissolved in demineralized water. Put on a pair of gloves. Pick up the conical flask and place it on the magnetic stirrer. Transfer the contents of the weighing dish to the conical flask. Use the measuring cylinder to transfer 50 ml of demineralized water to the conical flask. Place a magnet in the conical flask and turn on the magnetic stirrer. Dispose of your gloves. Why is it important to use demineralized water? That's right. Regular tap water contains many different ions from the minerals which are naturally contained in it. In this case, the chloride ions from the tap water would interfere with the analysis that we are performing. While we wait for the sample of unlabeled chemical to dissolve, let us find out how much silver nitrate we should add. In a gravimetric analysis, we want to precipitate the ions we are analyzing for as an insoluble salt so that we can weigh them. In order for the gravimetric analysis to be valid, we want all of the chloride ions to precipitate. How can we ensure this? Yes, spot on. We should add more silver ions than chloride ions. When the silver ions are in excess, we can be sure that all the chloride ions have reacted. Look at the reaction schemes in your journal. How does the number of moles of silver nitrate correlate to the number of moles of the alkaline earth metal chloride? No. This is incorrect. Please try again. Compare. Yes, you are right. You can see from the balanced chemical equation that one molecule of HCl2 reacts with 2 molecules of silver nitrate, so you should have twice as many molecules of silver nitrate. Now you can find the number of moles of silver nitrate to use by multiplying the number of moles of beryllium, magnesium and calcium chloride by 2. Fill in those numbers in your lab journal. Click the yellow field in the lab journal to calculate the number of moles of silver nitrate to use in each of the 3 cases. How many moles of silver nitrate should we use to be sure that we have excess, no matter which of the 3 compounds it is? That's right. Even the 0.075 moles would be enough to ensure excess if the unknown compound is calcium or magnesium chloride. We still need 0.100 moles to ensure excess in case the unknown compound is beryllium chloride. The silver nitrate has already been dissolved in water with a concentration of 1.0 mol per liter. That means you should use 100 milliliter to get 0.100 moles. Put on a pair of gloves. Use the measuring cylinder to transfer 100 milliliter of the silver nitrate solution to the conical flask. Did you notice the change? The solution went from clear to opaque, which means that something has precipitated. That is silver chloride, your product. Now you should filter, dry, and measure the mass of the silver chloride formed. Then you can calculate how much chloride was in the solution to begin with. Set up the equipment for a section filtration. Turn on the in-house vacuum system by twisting the knob. Squirt a little water onto the filter paper to make it stick to the funnel. Filter your product. Your product should be dried on a watch glass in the oven. Tear the watch glass before using it. Place the watch glass back on the workbench. Wash the filter cake with demineralized water. Transfer the filter cake from the funnel to the watch glass. Place the watch glass in the oven. Dispose of your gloves. Now your product is drying in the oven. While we wait for it to dry, let's calculate the mass of the product you would obtain in each of the 3 cases. Look at your lab journal. Can you see from the reaction stoichiometry how the number of moles of silver chloride formed correlates to the number of moles of silver nitrate consumed? Yes, spot on. The number of moles of silver chloride formed is the same as the number of moles of silver nitrate consumed. Click on the yellow field in the lab journal to fill out how many moles of silver chloride is formed in all 3 cases. Now that you know how many moles of silver chloride would be formed in each of the 3 cases, you can calculate the mass of silver chloride that would be formed. Pick the right formula in the drop-down menu to calculate the mass of silver chloride formed in all 3 cases. Yes, you've got it. Remember to perform the calculation in all 3 tabs. Yes, exactly. Yes. You are very good at this. What you just calculated is called the theoretical yield of the reaction. This is the amount of product you would obtain if the reaction went to 100% completion and you recovered all of the product with no loss. In practice, the yield will probably be somewhat lower, but let's see. Alright, the precipitate should be dry by now. Let's get it out of the oven and determine its mass. You should note the mass in your lab journal. Put on a pair of gloves. Remove the watch glass from the oven and place it on the balance. Dispose of your gloves. Note the mass of your product in the yellow field in the lab journal. What you just noted is the experimental yield of the reaction. Compare the experimental yield to the 3 different possible theoretical yields you calculated. Which of the compounds do you think it is? You were very accurate with the experimental procedure, so I would expect the yield to be more than 90%. Yes, you are right, it must be magnesium chloride. The mass of product you obtained is less than the theoretical yield, but not by much. Don't worry, that is very common in lab experiments. Note the identity of the unlabeled chemical in the lab journal. Yes, you are right. The compound is magnesium chloride. Now you can calculate the percentage yield of your reaction, that is the experimental yield divided by the theoretical yield times 100%. Pick the correct formula in the lab journal to calculate the percentage yield. Yes, you are right. So you obtained 93% yield of the silver chloride. Which of the following answers is not a valid reason for the percentage yield of the reaction being below 100%? That's right. If the product still contained water, its mass would have been higher than expected, and the percentage yield would have been above 100%. Excellent! You have completed the experiment. That was all for the simulation. It has been a pleasure having such a bright student here. Never mind about the cleaning, I'll have my assistant Roger take care of it. Your score has been saved together with your 100% progress. Congratulations, you have completed the simulation. We hope you enjoyed it and you feel wiser now. Press exit to close the simulation. This will open a survey. Please take 1 minute to provide your feedback. It will help us to improve Labster. I gain relevant knowledge by using the simulation. I found the simulation motivating. I feel more confident about my lab skills after the simulation. I feel that I can apply what I have learned in the simulation to real-world cases. In general, I was pleased with the simulation. Thank you for your feedback. Please exit the lab by pressing escape. See you in another lab.